So I'm really honored to be part of this celebration. It's my first visit to IPMU, and I salute the institute, its leadership, and the scientists on the remarkable, truly remarkable success of their first 10 years, and wish them many more decades to come. And I'm particularly impressed by how they integrate the experiment, the theory, and the theoretical theory within one institute, one beautiful building. And so I myself am a mathematician. I'm from the theoretical theory part of that spectrum. And it's not a secret that mathematics depends vitally on input from physics, and both theoretical and experimental, particularly theoretical, of course. And it's not just we draw inspiration, ideas, new problems. Of course, and I and my colleagues, we all of us learn a lot from Aguri-san, Hori-san, Tachikawa-san, and other remarkable people you have here. But it's also on my personal level. It's very important for mathematicians to feel I'm not sure what the word. I'm searching for the word. To feel like needed by the larger science community, because it's not so. In math, we have our own complexity. Math is extremely complex, and I'll be pointing at some very simple pictures, but of course, the actual math we do in our day job is as complicated as the inner workings of these big experimental machines that do these marvelous things. Except our math maybe doesn't do quite as marvelous things. But anyway, it's extremely complex, and our ability to explain it even to our colleagues is just as low as your ability to explain the inner workings of your big, large machines within the space of a public talk. And so when we see, so we've learned to embrace it, and we take certain pride in taming the complexity. But when people that think about the fundamental physics problem are drawn to the same set of questions, then it really adds to the self-esteem and the confidence that we're doing something right. So So this is after this long preamble, I want to talk about somehow the world beyond wall crossing. But most of my talk will be about actual walls and wall crossing, and then at the end I'll say something. So the subject of the ideas, mathematical ideas of stability, its variation, the walls, where that in the space of variation of stability, and the wall crossing that happens as you cross these walls, have been playing an extremely important role. As if I'm reading from my slides, which I'm not. I guess I was thinking about my talk for too long, I think. So anyway, they've been playing an extremely important role in mathematics, and maybe one of the most spectacular examples of this is the work of Todo-san right here at IPMU. He proved remarkable things about Donaldson-Thomas invariants and how they will cross for Calabi-Yau threefolds, and many other things too. Of course, I won't be able to explain any of that here in the span of 25-minute general audience talk, but I give you a baby example of what it means, what stability means, and how it changes. And this will be, so first, sorry, before that, so pictorially you should think about it. There's some parameters, maybe parameters for physical theory or theoretical theory, and depending on these parameters, an object remains stable for a while, and then it hits the wall of stability, becomes unstable, and the goal is to determine what are the in what other things it will decay as that happens. And so the basic example, this would be, I apologize, it would be like one math example in the talk, and will be really basic. Everybody will be able to understand it. So it's an example when I have something acted by a group, such as a group of gauge transformation. And I'd really like to form a quotient by the group action. So in physics, this is familiar. You identify, you say that somehow different physical systems are equivalent if they differ by a gauge equivalence. So then it just really describes the same physics. So this is what really matters is the set of all possible configuration modulo some equivalence. And so you may want to say that I'd like to consider that quotient be the set of all orbits, all equivalency classes under the group action. Well, that turns out, for reasons I'll explain in a second, not such a great idea. You shouldn't really consider all orbits. You should only restrict yourself to the set of stable orbits. And this will be an example explaining what this means. And the example will be it's a 2x2 matrices. In fact, 2x2 diagonal matrices. So if I take a two-dimensional, it doesn't matter for this example if it's a real two-dimensional space or complex two-dimensional space. And I will act upon it by 2x2 by diagonal matrices. Z is some number, could be real or complex, and Z inverse is what this introduces. And the general orbit, if I take a general point and move it under this group action, it will sweep this hyperbola. X, y equal a constant. And a nearby point will sweep nearby hyperbola. So these orbits are okay. These are the generic orbits and they'll look okay. However, if among all these hyperbolas there is the coordinate cross, there is x, y equals 0, and that's actually a union of 3 orbits. So if you scale by diagonal matrices, of course the origin stays the same. The vertical axis is one orbit, and the horizontal axis is the other orbit. And so what's obvious problematic feature of that is that a point on the blue axis can be brought arbitrarily close to this black dot by my equivalence. So there's no way to, they're not separated by anything. They can be made arbitrarily close. And this reflects in the picture that if I try to pictorially, of course, the set of all orbits looks like the C line in the equation x, the line of hyperbolas, the xy equals cc is my parameter. And the general point on that line corresponds to one single orbit, so this is good. However, at the origin, I have these 3 things. So at the origin, when xy equals 0, I have the origin, I have the blue one, and I have the red one. And so these three things, trying to sit, the 3 people bought the ticket for the same opera seat. It's not a good situation. And the solution to that is to declare only one of them to be stable and the other unstable, and therefore discard. And one way it can be accomplished, so this is actually, the one way it can be accomplished is that you can form this quotient by imposing an extra equation and then dividing by a smaller group. So this extra equation has some physical meaning. If you know what it is, it's great, but maybe I don't want to go into discussion. So instead of acting by all diagonal matrices, you restrict to diagonal matrices where absolute value of z is 1. But the extra equation you get is that you get to restrict the absolute value square of x minus absolute square of y to be equal to something. So let's see how this works here. If I make this number r positive, I'm getting this hyperbola here. And you see it hits all orbits exactly right. And it hits the red orbit, doesn't hit the black or the blue orbit. And so this really does provide a coordinate chart on my quotient. This would be one chart, so when this r is positive. If I could take, of course, I could take r negative, there will be a different chart, and that chart hits the blue line, it doesn't hit the red line, so another good chart, and selects one. In other words, from this coordinate cross, it select one good orbit, one stable orbit. And so then in other words, between these 2 things, is I vary r, which is actually a parameter in somehow. When we get there is some parameter in my physical theory. There is some, or in some theoretical theory, there is a wall. Something happens between r bigger than 0 and r less than 0, and there's the same quotient r is given by 2 different charts, and in one chart, this thing, the red orbit is stable, and the other chart is the blue orbit is stable. Is that clear? Since this is it's kind of an important point, maybe I'll grab my water bottle, which I forgot anyway. Oh, there is one. Yeah, good. Right. So, so what was important in this case is that my group that was determinant one. So I apologize for this undergraduate mathematics, but this is. Well, I think it's good to understand some examples which can be understood completely, because then many much more, like million more complicated examples, I can just hand wave through them. And so the reason is that the reason this is important is that so it was important here that this preserved the volume, the determinant of this matrix was equal 1, because if I consider some different action, instead of acting by z and z inverse, I act by z and z. The orbits would be all just raised through the origin, and then by the similar procedure, instead of this +1 here, will translate into the plus sign here. So instead of, I could still fix the absolute value square of x plus absolute square of y could be r, and there will be a very good chart for this orbit, and we'll exclude the unstable orbit at the origin. We'll have the interesting feature that on the other side of that wall, when r is less than 0, just nothing, just no stable orbits whatsoever. So the quotient is just empty. So the wall crossing in this situation is from a very nice quotient to an empty set, which is not what we want to do. In fact, in the situation we're going to discuss, this will be, in fact, this group G will not only preserve volume, will act like this canonical transformation in classical mechanics that preserve the symplectic, they're stronger that preserve the volume. So, in any case, that parameter r, it also has the meaning of the size of the quotient. So there's some, if we'd like the set of the orbits, we would like to think of this as Riemannian manifold, for example, and then it has a certain size. And since I'm giving you certain charts, the natural metric on those charts gives you size, and that's of course cherry. So of course it's evident with the circle example that if I vary r, that varies the size of thing varies. And this is, in general, this is what's called Kähler moduli, and in general it's a vector. It measures how different minimal surfaces in your what are the areas of different minimal surfaces in your manifold. And this would be important because we will, in a second, we'll be talking about sigma models with target this quotient manifold. And then the weight of a minimal surface, the holomorphic surface there will be an instanton in this situation. And it will be weighted according to its area. So that area is a vector, really. And what we would, the things we would really like to study is that is Higgs vacua in certain gauge theories, which have the same structure. It's something, it's a quotient of something by the group, and namely something are the configuration of my matter fields that sit at the bottom of the potential, and you mod out by constant gauge transformations now. And we study this not just supersymmetric, but large supersymmetry gauge theories in which these moduli spaces are really, really nice, and they wall cross nicely as the parameters of my gauge theory change. And I'm using this as really as a kanji for nice wall crossing, because these are very complicated manifolds of arbitrarily high dimension, and in fact, among them one finds the very sophisticated variety. Among them one finds, for example, Nakajima-Kruger varieties, and this is a recent, very exciting addition to IPMU already stellar list of faculty, which again I congratulate IPMU leadership and University of Tokyo leadership, and this is anyway. So right, and And so, like I said, these Higgs vacua, they depend on parameter in the theory, and they change really nicely. They flop, in the sense I've tried to convey by my example. And there's a general philosophy of another IPMU luminary, and with Orlov and Kawamata, says that if algebraic varieties flop, then they may not be isomorphic, but they're as isomorphic as close as two algebraic varieties could be. In fact, they share the same. They have the same complex of coherent sheaf. Okay, that may not sound so particularly concrete if you're a physicist, but the meaning of this object that they are if you study, so the gauge theories we want to study are in 2 or 3 dimensions, and in 2 dimensions these are the boundary conditions for your gauge theory. So the boundary conditions for the gauge theory will be the same, and then there will be line operators like analogs of particles really. In 3 dimensions, they'll be the same. So, but the point I want to make here is that while seems like as the parameters of the theory change, these interesting physical quantities don't. But in fact, it's not true. In fact, the interesting physical quantities change in a way that itself exhibits this kind of wall crossing. So this part of the talk is where I have more and more walls being piled up in front of you. But so this is really, again, this is an important thing. And that, so this is, I have this kanji here, which represents one of my moduli spaces of vacua, and then another one which is with different values of parameters in gauge theory. So this is the flop of that one. And in fact, instead of identifying physical, like stable, like whatever the line operators in your gauge theory or boundary condition in 2Ds, instead of identifying them canonically, in fact, there are many ways to go through this wall, and they give different results. And so if you're suspicious of how can this be true, I'll explain what it means numerically in a few minutes. And in fact, before I say that, there is an interesting, very beautiful picture of that by Bezrukalnikov and Kaledin. And it says that this multitude of different identification between theory here and theory there, it has to do with the fact there is an intermediate object, which is a certain quantum object, which is really, it's like a quantization. These are, since I've insisted the group action is by symplectic transformation, this object is by itself a symplectic manifold. It's like a phase space of classical mechanics, so it can be quantized. And the path from here to here goes through quantization. And that quantization itself has a certain, this is also like an algebraic variety. It has its own flop structure, which is in fact richer than what you see. Here you have just, so to speak, 2 or finitely many. Here you have countably many that form like a, they index by like a paving of some n-dimensional space. And as you go through this intermediate thing, you get different equivalences between here and there. And this is, incidental, these things form some structure also of IPMU fame. We'll come to that later. And so, do you think somehow mathematical physics is about numbers? Now it's time to turn to numbers. And I'll explain with numbers what this beautiful picture means. With numbers, it means the following: that as customary in supersymmetric theory is to compute various somehow suitably twisted supersymmetric indices or some various instanton counting functions that are the most accessible versions of the partition function of your theory with given boundary conditions. And so then this becomes, so this is a function of boundary condition, and it's a function of all your parameters in your theory, including the scalar moduli that tell you how big that manifold is. And in that scalar modulus, the analytic functions for large, somehow large. So here my real part of my kernel, here R, you should think of R being like the real part of kernel module. Here it's large, I get this. I'm in this regime. Here it's small. I'm in this regime. So I have an analytic function, and I can analytically continue it from here to there. And so that what I'll see is that the first feature of that, I'll see branch points at zero size. So this is zero, means I've the sphere in my manifold shrank to zero size. But there is, since I'm doing analytic functions, I can look at the imaginary axis. And the imaginary axis, there'll be some branch points here. And so then through between these branch points, I can try to go from here to there, and similarly from here to there. And it's actually a theorem that if you continue this function from here to there or here to there, you get the same. It's the same analytic function, except it's a vector valued function. Depends on boundary conditions, and the identification of the boundary. This is the same function, except you have to make change in this vector space, and that vector space is what this Bezrukhovnikov-Kaledin identification does for you. So this is in other words, this is a statement about function. And if you think about this, if you have an entry here that corresponds to a particular boundary condition in 2D, so it's like then this cell up here will be a linear combination of two different ones with coefficients computed by that theory. And in particular, the branch points along the imaginary axis are precisely the walls in that quantum in this. So the branch points here are precisely these walls here. So this actually kind of a complicated theorem to prove. It's been so it took us a long time, and one of the main technical ingredients came from a paper I wrote with Mina Aganagich, and where we solved the same analytic continuation problem, but in greater generality, namely we solve it for three-dimensional gauge theories. And so now, one more time, what is being counted? So I have a certain supersymmetric three-dimensional gauge theory that I consider on a space-time of the form just Euclidean plane across a circle. At the boundary of this Euclidean plane, I impose certain boundary conditions, and then inside of that, I can have the analog of an instanton. There will be a holomorphic map from this viewed as a complex plane going to this moduli space Slovakia. So this is so that's the usual thing when you at lower energies you approximate the states of your system by modulated vacuum. Right? So here the supersymmetric state is a holomorphic map from the space, and this being time, from the space to the modular space of vacuum, and the boundary condition says what this map does at infinity. So I can count this, weighting appropriately with the metric of M, and also is discussing in the theory, count them also equivalently really with the action of the orthogonal group in 2 dimensions. So this has, and there's also some flavor equivalent with respect to flavor symmetry. So it's a very multivariate function. And so now we would like to take this function, analytically continuing Kähler variables from here, from a theory to a flaw. And so what we find is that if I start with some Kähler variable, I analytically continue, I get a single valid function, which is now, instead of branch cuts, gets this sequences of poles, arithmetic progression of poles. That's not so surprising. What's surprising is that we can, so the fact that there's the branch cut, well, if you previously had a branch cut, you're now going to get one dimension up, you're going to get a sequence of poles. This is not maybe, will not exactly surprise you, but it's, what's interesting is that if I now compare analytic continuation from here to analytic continuation from there, so to speak, take a ratio, then I get one elliptic matrix with my domain being epsilon here and 2 pi I there. And that one object contains all Bezirkov colliding things as special cases. So this is, there's one, instead of this multitude of wall transitions, you get one elliptic function that depending, that if I degenerate my elliptic curve, send that epsilon to 0, then depending on the imaginary part of lambda, I'm getting different matrices. I'm going to get different, so from this elliptic matrix, I'm going to get different constant matrices. And all these matrices, I'll precise it, is this matrices one can compute from the previously discussed wall crossing. So an elementary point is that if you're looking for a piecewise, if you see a piecewise constant function, maybe it's a limit of an elliptic functions as the elliptic curve degenerates, because it's well known, it's kind of elementary, that if you study an elliptic function as one of the periods shrinks to 0 or expands to infinity, then in fact you have a piecewise polynomial, piecewise constant asymptotics, and you can see here in this plot, you can see the walls forming. And so what happens here is that our transformation, what it really does, it goes from elliptic homology of Higgs branch at one value of parameters to elliptic homology of the other, and identify them in the way that may be seen as a Weyl group element in a certain elliptic quantum group. And of course, another very exciting, relatively new addition to IPMU stellar research stuff is the father of the whole idea that the elliptic quantum group should act on elliptic homology, Kapranov's-son, who also the Schober thing is also here, I think, is another one of his creations somehow. This is, and maybe the very idea, so you think about this, the very idea that the groups should have generators and relations is really some kind of wall, has a wall crossing flavor to them, and in particular for that kind of discrete wall crossing thing. So that wall crossing thing was so in 2 dimensions. What is relevant that there's some algebra was generated by dots in this picture, and then if you draw different lines in that picture, you'll see different rank 1 subalgebras. Such as you take a Weyl group element in that rank subalgebra, it gives you different Bezirkov collision monodromies. But in reality, there is one elliptic object that contains them all, and contains all of this as different limits, and it contains this algebra in the sense that the elliptic quantum group doesn't really have generators in relation, some continuous analytic object, and upon some degeneration, it gets you generators and relations like this. And of course, the next step is to really make it the Bezirkov collision work, and Bondel-Arlovka-Amata conjectures are not about, I was talking about really results in K-theory and elliptic homology there, but they're really results about derived category coherent sheaves. And this is what I think is true, and what we're somehow working on now is that really what should really be true is that there's a bigger category here. There, instead of the category of boundary conditions in 3D, so these are categories of, instead of finitely generated modules over functions. So I apologize, this is not meant for general audience. There are now finitely generated modules over some real big algebras, certain algebras of like vertex operators of your manifold, and that they all can, just because of their symmetries, they all contain the grading operator L0. And if you grade them, if you consider that grading by Q, you get really objects on like a Tate elliptic curve, and as that Tate elliptic curve degenerates, you go here. And then the point of that would be that the multitude of different equivalences here is really covered by one element here. So that's the, and so maybe that's the main message, is that there is a world where elliptic quantum groups and elliptic homology rule, and you don't. There's really no walls. The walls are all in how you take the limits from there. So that's what I wanted to say.
Thank you, Andre. Okay, so now time is open for question or discussion. So anyone has any question to Andre? Okay, Robert.
So I have an old-fashioned, simple.
Please wait for microphone, Robert.
I have an old-fashioned, simple question. Thinking back to the 60s and regipoles and analytic continuations. So you remark about branch points. And often with analytic continuations, there's branch points and branch cuts. And if you're going to do the integrals, you have to find your pathway around them. So this implies some kind of spectroscopy, some kind of spectrum associated with the groups and the operators involved. Is that an appropriate way to think about this? And if there are branch cuts, as opposed to just branch points, then how do you manage around the cuts?
Yeah, so as you go around the cuts, precisely you get the monodromy. Means your function comes back with itself with some transformation, and the transformation is precisely captured by. So in other words, maybe this is okay. This doesn't work. Oh, here. Maybe I'll go here. So this is there's some vector valued function here that as you analytically continue, that you come to another. So you want to express it in some basis that now has to do with this point, and the expression in this basis is exactly tells you how something what was stable here decomposes in things that was stable there. So that is with appropriate coefficients. And the coefficients now, of course, since we're counting everything, so everything is charged under some big group. Everything is now with coefficients being representation of that group. So that's but it really, even when you mention spectroscopy, it's not unrelated. Yeah, it's really.
Okay, so let's thank Andre again.